Hello everyone, welcome to the Bodhi Academy. In today's PYQ series, we are going to solve PYQs of 12th Chemistry, chapter D and F block elements. So let's solve the first question. Write the electronic configuration, ground state of scandium 21, titanium 22, chromium 24 and copper. Explain any exceptions. So for scandium, we have atomic number 21. So the EC will be argon 3D1 and 4s2. For titanium, the atomic number is 22. So it will be argon 3D2 4s2. But for copper and chromium, there is a slight exception. So for chromium, the atomic number is 24. So it will be argon 3D5 4s1, and for copper the atomic number is 29, so it will be argon 3d10 4s1. Here the d orbitals will get filled first because the half filled d orbitals and the fully filled orbitals will provide extra stability in the ground state to the elements. Coming to the next question, give two examples of each of common oxidation states of iron and manganese with one reaction illustrating each element in two different oxidation states. So we have two different oxidation states of iron, that is Fe plus 2 and Fe plus 3. So the example is redox reaction where Fe plus 2 gets converted to Fe plus 3, or oxidation by ferric ion. So it can be written as Fe plus 2 plus gives Fe plus 3 plus 1 electron. So manganese have two oxidation states, Mn plus 2 and Mn plus 7. So acidified, example is acidified KMnO4 oxidizes Fe plus 2. So that is MnO4 plus 8H plus 5 electrons will have Mn plus 2 plus 4 molecules of water. And the second half reaction is Fe plus 2 gives Fe plus 3 plus 5 electrons. So overall this reaction is MnO4 minus plus 8H plus 5 Fe plus 2 gives Mn plus 2 plus 5 Fe plus 3 and 4 molecules of water. Let's move on to the next question. Explain the geometry and origin of color in the complex ion CuNH3,4, the whole 2 plus. So geometry of this compound is square planar for Cu plus 2 complexes with strong ligand field in many cases, or distorted octahedral in John Taylor distortion, commonly observed as flattened octahedral leading effectively to a square planar behavior. Color origin, Cu plus 2 has partially filled d orbitals and visible color arises from dd transitions, electron promoted between split d orbitals by ligand field and sometimes charge transfer. In Cu NH3,4 plus 2, the complex is deep blue due to partially allowed dd transitions and ligand to metal interactions. Coming to the next question, calculate the magnetic moment, spin only, of Fe plus 2 in a high spin octahedral complex. So we have iron. So the atomic number of iron is 26. So argon 3d6. But Fe plus 2 has 4 electrons. So the electronic configuration becomes argon 3d6. So here the number of electrons, unpaired electrons, is 4. So the formula to find the magnetic moment is mu equal to root of n plus 2. So the n value we got is 4. So 4 plus 2, that becomes root 24. So the value of root 24 is 4.8989. So which comes up to 4.9. Coming to the next question. What is lanthanide contraction and state 2 consequences of lanthanide contraction in chemistry? So lanthanide contraction it is the progressive decrease of ionic radii of trivalent lanthanide ions despite increasing the atomic number. So it is due to the poor shielding effect of the 4f electrons increasing the nuclear charge that pulls the electron closer. So the consequences is similar ionic radii of some 4D and 5D elements and difficulty in separating these elements. So it is a industrial separation challenge. Also, increased density and hardness across the series affects the chemical behavior. So that is example is comparable sizes of La plus 3 and Ce plus 3 affects the complex formation. It causes higher than expected complex stability and similar radii of 4D and 5D metals. Chemical properties of 5D element resemble corresponding to the 4D elements. Coming to the next question, why Zn plus 2 salts are generally colorless while many transition metal salts are colored? So Zn plus 2 has electronic configuration of argon 3d10. So it has completely filled d orbitals. So there is no dd transition that requires partially filled d orbitals because here the d orbitals are completely filled. So there is no available low energy DD excitation, so DD colors are absent and any color would come from charge transfer transitions. Therefore, Zn plus 2 has no color. Coming to the next question, write one reaction where D block metal acts as a catalyst and name the catalyst and the process. So first example is Haber's process, that is N2 plus H2 gives NH3. So in this process, uh, the catalyst is iron and it is promoted with K2O and Al2O3. Another process is contact process, that is 2SO2 plus oxygen gives 2SO3. Here, the catalyst that is used is vanadium oxide, that is V2O5. Now, these transition metals are used as catalysts because D metal provide vacant d orbitals for absorption and activation of reactants, therefore lowering the activation energy. Coming to the next question, balance the redox equation of acidified KMnO4 oxidizing oxalate ion, that is C2O42 minus to CO2. So we have the oxidation reaction, that is C2O42 minus, which gives 2CO2 plus 2 electrons, and we have reduction reaction, that is MnO4 minus plus 8H plus ions plus 5 electrons gives Mn2 plus 4H2O. So 5 and 2 electrons, so we take the LCM of 5 and 2, that will be 10. So we'll have to multiply 5 to the oxidation reaction and we'll have to multiply 2 to the reduction reaction. So multiplying 5 in the oxidation will get 5 C2O4 2 minus gives 10 CO2 plus 10 electrons, and here we'll have 2 MnO4 minus plus 16H plus 10 electrons gives 2 Mn plus 2 plus 8 H2. So overall we can write the reaction as 2 MnO4 minus plus 16H plus 5 C2O4 minus gives Mn 2 Mn plus 2 plus 10 CO2 and 8 H2. Coming to the next question, why do actinides show a large range of oxidation states than lanthanides? So actinides 5f orbitals are more extended and less tightly bound than 4f orbitals of the lanthanides. So 5f, 6d and 7s electrons can participate in bonding. This leads to multiple accessible oxidation states. Lanthanides have buried 4f electrons that are poorly available for bonding. So they mainly show only the +3 oxidation state. Coming to the last question, you are given a mixture containing Fe plus 3 and Al plus 3. Suggest a simple chemical test to distinguish between them and write the reactions. So test with NaOH is the one to use here. So both Fe plus 3 and Al plus 3 gives hydroxide precipitate on reacting with NaOH, but the results will differ if you use excess of NaOH. So Fe3 plus on reacting with NaOH will give you iron hydroxide, FeOH3, Al plus 3 plus 3 OH minus will give you AlOH3. But in it is a the AlOH3 is a white gelatinous precipitate and FeOH3 is a brown red precipitate. So this brown red precipitate is insoluble in excess of NaOH, but the white gelatinous precipitate of aluminium is soluble in excess of NaOH. So if you add NaOH dropwise, both the compounds will form precipitates, but in excess of NaOH, only the Fe plus 3 will be present. That precipitate won't be soluble. Alternative test for this is KSCN thiocyanate test, which gives blood red complex with iron, but it gives no color with aluminium. That's it for today's video. Don't forget to like, share and subscribe to the Bodhi Academy. Thank you.